Good morning, everyone. So what I'm going to present this morning is a work on the use of machine learning strategies for, this case, in memory execution of data-intensive workflows. So this is a joint work with my colleagues Riccardo Cantini, Fabrizio Marozzo, Alessio Orsino, and Paolo Trunfio. So what is the idea here? Just to introduce the idea. We often, or more often than before, we have today data-intensive workflows that are used to orchestrate complex set of tasks that handle and process huge amount of data. You know, this happens obviously in many scientific tasks, but also today in many AI applications. So for us, a data-intensive workflow is a sort of computational process that involves significant processing steps that are based on big data processing. So big data acquisition, transformation, big data analysis, results, storage, management, and in some cases, visualization. So what we try to do is to use techniques, in this case based on machine learning, to reduce the execution time of these data-intensive workflows, in particular to reduce the usage of disks or usage of memory in general, to speed up this the execution of this workflow. So the idea is try to learn about the execution of this workflow for trying to avoid or to limit the usage of disk storage. Now, to do that, what we implemented is called the intelligent in-memory workflow manager that helps to optimize the in-memory execution of this kind of data-intensive workflows on parallel machines. So what are the main components, the main strategies of this approach that we are implementing? So we have two complementary strategies. One is to have a machine learning strategy that try to predict the memory occupancy and the execution time of workflow task. After that, we designed scheduling strategies that exploiting the machine learning knowledge. So what we learn from the analysis of the workflow to allocate tasks to computing nodes, taking into account the predicted memory occupancy and the execution time of each task, and obviously globally of the workflow, and also to consider the memory available on the nodes where the tasks are executed. We implement a prototype of this system based on these two strategies, and we access it. So we run some experiments to assess the effectiveness of this sort of machine learning based predictor together with this scheduling strategy. I will show you at the end of my talk a few results, even if there is no time to go in detail on all the results we got, but just to give you an idea of what we can obtain with this approach, I will show you some results. Now, so what is the goal of this workflow manager that we implemented? So the idea is to improve application performance, as I mentioned before, through adaptive usage of memory resources. So this is carried out by identifying cluster of tasks that can be executed in parallel on the same nodes, on for example, on a set of cores of the same computing node, trying to optimize the memory processing to limit or avoid the use of this storage. So the idea is try to identify the amount of needs for memory, for main memory, and try to allocate this task on the node that may provide main memory to satisfy these requirements. So skipping the requirements for the usage of the disk that obviously may reduce the scalability and increase the execution time of application. So given a data-intensive workflow, the manager we implemented exploit a sort of meta-learning model for estimating the amount of memory required by each workflow task and to estimate also the global execution time. Using this knowledge that we acquire from the analysis of previously executed workflow, we inform the scheduling strategy to have a sort of optimal schedule for the execution of the workflow. So now, I mentioned before the so-called meta-learning model. In this case, we have a set of regressors and plus a decision tree at the end that put together the results of many regressions we run. So this meta-learning model is trained on a log of past executed workflow. So this is the past knowledge that we exploit to improve the execution of the workflow. So in the meta-learning model, a set of relevant features of the workflows are considered. For example, here I list some, perhaps the most important. So one is, for example, the workflow structures. So how many tasks compose the workflows, which kind of data dependencies exist among the tasks, so the way in which the tasks interact with each other. Other than we consider that, since we are in the area of data intensive workflow, the input data size and the input data format. So not only the dimension, the size of the data, but also the structure of the data that we need to process. So the number of rows, the dimensionality. For example, in data analysis task, it's important to consider the number of features that must be analyzed. So both the number of rows, but also the number of columns and other features that may describe the complexity of the input data. At the same time, we consider also the types of tasks. So for example, the computation that is performed by a given node of the workflow, so by a given task of the workflow. So in case of data analysis workflow that we run in our experiments, for example, we distinguish it among the kind of task we run, the kind of algorithm, for example, an unsupervised algorithm or an association rule discovery task or other supervised learning algorithm and other data processing algorithm. So considering these features, we define a sort of model for the execution of a workflow. And predictions made for a given computing node, a given parallel server, obviously are not applicable in general, but are applicable to all similar computing servers. So in this case, we consider the features of the hardware on which the task of the workflow are run. So in case we have system with the same architecture, with the same type of processor or the same operating system, memory, devices and sites and so on, the prediction are still valid and could be reused for other workflow execution. So this approach makes the proposed system, the proposed manager, usable on large-scale homogeneous high-performance computing system. So many identical servers. As a future work, we are considering to study also heterogeneous HPC system, but at the moment we have no result on that. So, given a data-intensive workflow, the workflow manager exploits the estimates coming from the machine learning model for producing a scheduling plan aimed at reducing minimum memory saturation events that can occur when multiple tasks are executed concurrently on the same computing nodes. Here you can see some figures about the accurateness of our learning model, in particular the combination of regression estimates with the decision tree with respect to the ground truth. So in this case, both for considering storage memory, execution memory, and also duration of the execution of a workflow, we may see that the prediction of this value are pretty well accurate. So at least in the example that we ran and we tested. Okay, in terms of approach, these slides try to summarize how our workflow manager works. So we start from a prediction model and from a workflow. Then the manager try to analyze the workflow with respect to the prediction model and produce a scheduling strategy, for that. So given a workflow and a prediction model, the system generates a scheduling plan in 2 steps. In the first step, there is the building of the stage of the workflow with task assignment. So here the goal is to avoid swapping to disk due to memory saturation. The second step is called stage consolidation. In this case, this step aims at reducing the number of stages by merging stage without dependency, so that can be run in parallel. And this is done according to the available memory. So according to the memory requirement of this task and the available memory of the nodes where this task could be or will be executed. So this is the approach, and what we did is try to run some experiments. In particular, the manager had been evaluated using Spark as a test bed. You know that Spark is a well-known and very often used framework for data-intensive application. So in our case, we evaluated the performance of our approach, the benefits coming from the use of the workflow manager on 3 workflow example. In particular, 2 are synthetic and another one is a real one. And we generated this data-intensive workflow as example for investigating specific scenario related to the presence of high-level parallelism and a limited amount of main memory reserved for execution. So what we did is to make a comparison between the result of the workflow manager with the blind scheduling strategy, which only consider workflow dependencies for parallel execution of tasks without any relation with data requirements and memory requirements. So I will not show you all the 3 examples that we ran, but I will show you one of them. In this case, we have a workflow which is composed of 27 tasks. The workflow is composed of 27 tasks that are highly heavy tasks. The execution of a single task can exceed the available memory. In particular, we configured one task, the T18, with an estimated peak memory occupancy higher than the Spark available unified memory. So we did explicitly that to show how the system tried to address this problem. So in this case, at least for this task, the memory will be saturated. So just to show you some results, in this case, you may see that the comparison between the disk usage in the blind full parallel solution in comparison with the disk usage in case of the workflow manager, and you may see here that in the blind solution we have high disk usage for a significant part of the execution, whereas the disk usage in case of the workflow manager is very limited. And in this case, the workflow manager cannot solve the solution, the situation, because we imposed to have a request of memory higher than the memory may satisfy. But at the end, for the rest, the disk usage was 0. So this is very interesting. And these results can be seen also if we look at the average peak disk usage in the same use case, and also in the average execution time. So you may see the blind solution and the workflow manager solution. So when the memory size is small, there is a very large difference in terms of disk usage. Obviously, this is reduced when the memory size increase. And the same occurs for the average execution time, that in our case is significantly reduced. So thank you for your attention. I'm going to conclude my talk. Just to summarize what we did, we feel that machine learning can be effectively exploited for optimizing the execution of data-intensive workflow. In this case, the intelligent in-memory manager we design is a good, at least on the basis of the experiments, is a good solution for optimizing the memory execution. The experiments results suggested on all the use cases we tried that by jointly using a machine learning model for performance estimation and a suitable scheduling strategy, the execution of the intensive workflow can significantly improve memory usage with respect to the state-of-the-art blind strategy. As a future work, I mentioned before that we will consider a heterogeneous HPC system, but also we consider also to invest to extend the information about task, input data, and hardware platform feature to be included in the learning algorithm to get more accurate results. So thank you very much. That's all.